welcome to SanfordFlipMath. We are working through the Algebra 2 course. We've been working in the Springboard book. We are now to what they call Activity 25, which works through graphing and solving square root and cube root functions. And what we're going to focus on in this video is about graphing square root functions, which we've actually done a fair amount of back when we did transformations, and then extending that to cube root functions. And I guess we need to establish what a cube root function is. So just a reminder, square root basically means what was squared. That's the meaning behind square root. And so, and if you recall, we are not going to take a square root of a negative number because there's no number we can square to get a negative number unless you go imaginary or complex numbers. And so for us, for graphing, and that's what we're focusing on here, is graphing and describing the graph. We're going to start at 0 because that's the smallest number we can work with. And what was squared to get 0? 0. 1. What was squared to get 1? Well, 1 was squared. I would do 2, but the square root of 2 is 1.4. It's kind of ugly. We don't like it. So we tend to stick to numbers called perfect squares, which are a little nicer to graph. So like 4, the square root of 4 is 2. And then the next one is 9. The square root of 9 is 3. And we don't need a million points for this. Usually we just kind of focus on those 3, and that works. So something like this, 0, 0, 1, 1, 4, 2, and that's probably good. And just a reminder that the background on this, where did this come from? Remember, again, this is saying what was squared. So if you start with the function y equals x squared, which is a parabola that opens up, and if you do the inverse of that, you may recall it reflects the graph over the line y equals x, this line, and turns the graph sideways. And we at that point discussed the fact that this is not a function, and so we kind of ixnayed or got rid of the bottom part and only kept the top part. So the shape of this thing is actually half of a parabola. It opens to the right unless we do goofiness to the graph, to the function. So this is a half parabola. Not that we're going to make a big deal out of that, but it's worth noting. And the domain of this, as we said, we can't do square root of negative and get real answers. So the domain of this is the x's have to be greater than or equal to 0. And if you prefer interval notation, that would look like that. And the range, it looks like we're only getting positive or 0 answers. So y would be greater than or equal to 0. And so again, we could say from 0 to infinity. Okay. If you need to pause here, pause, but this is just a quick recap of just the parent function. And then let's take this bad boy for a spin. I'm going to move to another function that looks just like this, only different. Okay. So remember some basic ideas about what happens here. We have some stuff going on with multiplication or division. Okay, remember that multiplication or division does stretches or shrinks. Remember that addition and subtraction do basically shifts or moves. Shift, slide. Okay, so shifts and slides were called translations. Stretches and shrinks were called scale changes. Okay, and then there was a special case of multiplication or division, and that's if you multiplied by a negative. If you multiply or divide by a negative, you get a reflection, and it totally depends on what variable where the negative is. If it's on the inside, it does things differently than on the outside. Okay, one other category of things to kind of throw in here, and then we'll actually do some work. Remember that anything that happens to the inside, we do the inverse. Okay, we did this all earlier this year. Inside, you do the inverse, and it affects things horizontal, or in other words, it's about x, something to do with x. If it's on the outside, Remember, you do what it says. It's vertical or about y. Okay, so all of this to kind of recap the basic framework, the basic rules of what we talked about back in, oh, I don't even remember where it was. I guess I should have looked it up before I started this craziness, but I didn't. So we did a lot of transformation stuff back in first semester, okay? So as we look at this equation, this function, notice the 2 is on the outside. So it's on the outside, we do what it says, it's vertical, it's about y. So there's a vertical stretch of 2, so it makes it twice as tall. Okay, and there is a +1 on the outside also, which is going to shift, move, slide, translate it up 1, do what it says, not the inverse. Okay. And then there is a -3 on the inside. Well, inside is inverse, so we do the opposite of -3 and say +3, so it's going to shift right 3. Okay. Just a quick reminder that anything dealing with multiplication or division must come before things that deal with addition or subtraction. So the vertical stretch of 2 has to come before that shift up of 1. Technically, the horizontal stuff is separate, so you could, I guess, do that whenever you want, but I'm going to just encourage you to do anything about multiplication and division first. Okay, so let's take this bad boy for a spin, and let me remind you that the parent function was at 0, 0, 1, 1, and 4, 2. So this is the parent function, okay? And so what we're going to do is I'm going to stretch this by 2 first. So 0, 0 is going to become 0, 0. And again, what we're doing is we are multiplying the y's by 2. So the y value for 1, 1 was originally 1, so now it's going to be 1, 2. Okay, so again, 1, 1 became 1, 2 from this 0, 0 became 0, 0 from the stretch. And 4, 2 is going to become 4, 4 because, again, we're multiplying the y values by 2. So you can kind of just eyeball things in here. And why am I doing that dotted? This is the Dora moment where I'm looking at you tipping my head back and forth. I did it dotted because we're not done. We still have to shift up 1 and right 3. So I'm going to do that now, and I'm just going to take the new points that I just did and go up 1 and right 3. Okay, so that used to be 0, 0. Okay, so 0, 0 is really now at 3, 1. I'm not going to do this for all the points, but just get an idea. Okay, so I'm going to go, again, right 3. This is now the 1, 2 point that I'm working with. So right 1, 2, 3, and then I'm going to go up 1. I don't know where's going on here because my, oh, yeah, well, that's probably good actually. Right 3 and up 1. Really? That's right 3 and up. All right. Let me back up because I feel like I got ahead of myself here. Okay, so at this point right here, no, this point right here, oh, that's what happened. 1, 2, 3, and up 1. I got distracted by the parent function there. I need to go back to the blue. 1, right, 3, and up 1. Oh yeah, that's so not beautiful. Why does that not look right? It's so not right. And I don't want to redo everything in this video. Sorry. It's, oh, because I'm supposed to start here. Come on. There we go. See, this happens to me too. Okay, well, 10 minutes in, I'm not going to start over. All right, so one last little question here, and that's domain and range. So notice where this starts, and that's a big deal. Remember, domain is about x's, and it starts at 3. So I'm going to say x is greater than or equal to 3. And again, if you are a fan of interval notation, there it is. Range starts at 1. Again, y values, so this is going to be y is greater than or equal to 1 because it starts at 1 and goes up. Okay. So again, if you want 1 to infinity. Okay, I know that's starting to get messy, but we're going to let it go at that. Okay, so this is square root. Okay, so what's different? Well, you should have seen this theoretically in Algebra 1, but I know real life doesn't always afford us those opportunities. What I need you to first see is that when you see this, this gets used so often that they don't bother to put a number there, but and I think in terms of the development, this came first. But the idea now is that if we do, technically there's like, you can pretend like there's a little 2 in there. So remember that this means what was squared. In other words, what was to the second power. Okay, well, this is called cube root, or it could be third root. And shockingly enough, it means what was cubed. Or in other words, what was to the third power. That's what this means. Okay, so there are perfect cubes, there are, just like there are perfect squares. And just so we're clear, yes, there is something that's fourth root. So what was raised to the fourth power? Fifth root, what was raised to the fifth power? What was raised to the sixth power? So that number inside there can be pretty much anything. Now, normally with this notation, it's limited to positive whole numbers. You know, usually we don't say what was raised to the 0.2 power, although mathematically there are ways to handle that. We're not going there. So our big focus is going to be on the cube root. Okay, what was cubed? And just like when we do square root, you know, we do things like, so the square root of 4, well, it's the square root of 2 times 2. So here's that squaring. And the idea is couples get to go out is the way I kind of teach this. So when you do the square root of 2 times 2, it just becomes 2. Or if you're doing the square root of 12, this is the square root of 2 times 2 times 3. Again, couples get to go out. Well, the same thing happens with cube root, only it's cubed. So it's triples. So like if I'm doing the cube root of 8, I'm looking for triples. I know this is awkward now, but we're just extending an idea. Triples get to go out. So the cube root of 8, cube root of 2 times 2 times 2 is 2. So if we were going to do something like the cube root of 24, well, this is, and I'm looking for that triple, so there it is. Now, our big focus here is not so much on you know, simplifying cube roots and things like that, although we probably should. Time is getting away from us. But we are looking for graphing, you know, how do we graph this and things like that. So there's a certain amount of plot some points that needs to happen here. One other little point of clarification that you may not like is, what about the cube root of -1? Is there a cube root of -1? Can you take a cube root of a negative? And I'm here to tell you that, remember that if you raise a negative to a third power, you do get a negative answer. If you raise a negative to the third power, you do get a negative. So I can do the cube root of -1, it's -1. I can do the cube root of -27, it's -3. Okay. So what that's going to do is it's going to mess with our domain and range a little bit. Okay. All right. So what I would like to do is use this opportunity to start a parent function for cube root. Okay. So let's do that. Now, let's just work with some points, I guess. Okay, so I'm going to start with 0. Now notice I stuck 0 down, way down in the middle, and there's a reason for that. Just kind of roll with it. What was cubed to get 0? Well, 0 to the third is 0. What was cubed, the cube root of 1, what was cubed to get 1? Well, 1 was. And we've seen 8 a couple of times. And I'm going with 8 because it's a perfect cube. The cube root of 8 is 2. 2 cubed is 8. And it might even be easier to work with the y value and say, well, 3 cubed is 27. So if I'm saying what was cubed to get 27, hey, I guess it was 3. That's kind of a sneaky way to do this, okay? The reason I started 0 in the middle is because, remember, negatives work also. Now, I'm going to suggest that we might want to work with just these points for a parent function. We might even only work with these once we get comfy with the shape, okay? But let's start out with the stuff in red, and let me put some little marks on here. Okay, so negative 8, negative 2 would be here. Negative 1, negative 1. Whoop, that looks more like negative 2, negative 1, sorry. 0, 0, 1, 1, 8, 2. And what we're looking at is this. Now, I just need to take a hot second here and remind you of something. If I take this y equals cube root of x, and I do inverse, sound it out. Nicely done, good job. If I do inverse, this becomes x equals the cube root of y. This is just for background. I just want you to see what's going on here. If I cube both sides now, this becomes y equals x cubed. Well, y equals x cubed, 0 cubed, 1 cubed, 2 cubed, negative 1 cubed, negative 2 cubed. What I need you to see is this blue graph and the black graph are inverses of each other. And we've been playing with x cubed for a while. We've been seeing that as we've been working through the polynomials. So there is a definite connection. This is that, again, reflection over the line y equals x when we do inverse. So I just want you to see that. Now, I'm not going to leave this here, so if you're interested in that, hit pause now, because I'm going to like undo, because that's really just a background connection that I want you to see. Okay, so here we go. It's like magic. All right, cool. All right, so this basic shape, this is not a parabola. It's not two half parabolas. The curvature is slightly different. It has a similar shape as a parabola, but it's not the same thing. But I just need you to kind of make a note of how it looks, okay? So I'm just going to put a little check mark there because I'm not going to call it anything except a cube root graph. So what about the domain this time? It looks like it goes forever to the left and forever to the right, so it looks like the domain is all real numbers. Now, as I go way, way, way to the left, it is going to keep going lower and lower and lower. I mean, not like that, but, and as I go to the right, it's going to keep going up and up and up. Every x value is going to get covered. Every y value is going to get covered. So you'll be happy to know that the domain and range are both all real numbers for a cube root graph. Okay, so time is getting away from us, but here's the deal. Everything that you learned about transformation still apply. So these are the same transformations that we just did with the square root. Okay, so there's a vertical stretch of 2, and it shifts right 3 and up 1. Now, to my fans of notation, you are certainly still welcome to do like the linear notation when it's a combination of things and say x plus 3, 2y plus 1. That's the mapping notation. And so remember, the parent function is going to look like this, and it's going through 0, 0, 1, 1, and 8, 2, and the negatives of those. Okay, that was kind of a backwards way to do that, but it actually worked pretty nicely. Okay, so I'm going to stretch it by a factor of 2 vertically. So that means that all of my y values are going to double. and then I'm going to shift it right 3 and up 1. Now I know I'm boogieing now because I'm worried about your time. Feel free to pause, feel free to, oh, I'm moving the wrong point there, caught myself. 1, 2, 1, 2, no, I'm doing too big I'm not on a grid, so this is problematic. So much for saving you time. Okay, so there, something like that. And then this point is going 1, 2, 3, and up 1. Up 1. Oh, that's rugged, but it'll have to do. Oh, that's terrible. All right, so we're already at 21 minutes. Again, domain and range were all real numbers, and when you shift them and stretch them, it's still going to be all real numbers. And I guess I'm just going to let it go at that. The rules for transformations are the exact same rules. The only thing that's really different is we are on a new parent function. Okay, so this is it for SanfordFlipMath this time. Thanks for hanging with, and we're out of here. Bye.